Okay, let's start. Hi everyone, my name is Raresh. I work as a tech lead in N26. For those of you who don't know N26 yet, we're a digital-only bank. We're available across Europe, UK, and soon the US. So yeah, if you're Polish, for example, you can open an account with us and check us out. But yeah, this is not what I wanted to talk to you about. Today we're going to talk about service-to-service call resilience. And before we start, I would like a show of hands. Which one of you knows Hystrix? Okay. Which one of you is using Hystrix in production? Okay, cool. So you're at the right place. But I have bad news for you. Hystrix is dead. So I think around October, Netflix announced that Hystrix is officially in maintenance mode, which means that it's only maybe going to receive security patches, but that's it. As a bank, we cannot really afford to take this chance, so we decided to get together and be like, okay, what do we do about this? And the first question we asked ourselves is, come on, this is 2019, who still uses synchronous service-to-service calls? So I'm going to ask you, which ones of you are still using synchronous service-to-service calls? Okay. Which ones of you have switched to kind of a mix between synchronous service-to-service calls and some asynchronous, whatever, Kafka? Okay. And which ones of you are the brave New World people that have gone fully Kafka, drank all the Kool-Aid? Okay. So we decided that it was pragmatic to actually go for a combination of both. We are heavily using asynchronous patterns, but at the same time, not everywhere was it meaningful and logical to actually use ditch synchronous service-to-service calls completely. So, for example, you have to build your entire UI around the assumption that you're async. If you don't have that, it's going to be tricky for you. We have a lot of our partners that we have to provide SLAs for, and when we're in an asynchronous environment, it's harder for us to actually make sure we're enforcing those SLAs. So there are many situations in which we still decided that going synchronous is the way to go. Okay, so whenever we discuss about synchronous service-to-service calls, we have to discuss about cascading failures, what they are, and how to prevent it. And this is what this talk is largely going to be about. And in the end, I'm going to talk to you about some tools that we investigated in order to replace Hystrix. Okay. What do you think happened here? And the question is vague because the answer is vague as well. So this is the number of read write-ups on an RDS. In this case, it's a Postgres. And at some point, something happened, and we have this massive spike. Anyone?
Bank transfers?
No, it's even vaguer than that.
Forever Retry?
No, it's change. So, as many of the talks at this conference said, change is something that's inevitable in our industry. And in this particular case, the change was someone was trying to replace some logic that was relying on a cache to fetch the country of a user. And product said, okay, we cannot afford the possibility of this cache being invalid, so let's just use this cache as a fallback mechanism, and let's try to always fetch the data from the source service. Unfortunately, they reused a piece of code that actually called this service to update the cache. So it did this update, it actually stored the information in the database, and after that, fetched it from the database. It's not a very nice pattern. And it meant that we had a huge spike in the number of write operations, which took us to this other scenario. This is just a zoomed out version of the chart I've shown you before. So what do you think happened here? You see this initial part where we had the deploy, and then there's this sudden drop. No. Usually deploys are marked with this pinkish line, so it wasn't a revert. We got throttled by AWS. You have this thing called burst balance in RDS, which kind of makes sure that you're being a good citizen and you're not overusing resources. It does give you some headspace if you have bursty traffic, but this can only go sometimes. So if you look at this, and this chart that's taken from the AWS documentation, it's exactly textbook burst balance throttling. So throttling by our providers is also some potential trigger for problems and eventually for a cascading failure. Okay, this one's nice as well. So usually the requests per second here are directly proportional with the traffic, with the logins that we get on our services. But you see these spikes coming in at semi-regular times. What do you think they are? Sorry? Nope. They're schedulers. So if you look at the time when this is happening, it's every 15 minutes. This I put under the general name of entropy. It's another trigger condition, and it's basically consists of stuff like bursty traffic, schedulers running. You can see that here we had an instance where we had bursty traffic, and during this scheduler run, we actually had to fetch a file from a third party, and this file was way bigger than we had expected. So, we got DDoSed just by fetching a file somehow. So it's quite a weird pattern. Yeah, your request profiles can change. You can get more data than you're supposed to. Organic growth can also lead to a lot of entropy. There's many triggers for this. So what this all boils down to is that we are using a finite set of resources. And if we exhaust any of these resources, we are in a situation where we can be in a potential trigger situation for a cascading failure, sorry. So if we run out of CPU, memory, Vespine gas, we might be in trouble. Okay, the thing is that these resources are also not independent of each other, and they're usually kind of connected. So let's just say that you came to Devoxx, you saw a really nice talk about garbage collection and about tuning your garbage collection for your JVM. So you take a good day, such as Friday, no one's in the office, afternoon, perfect timing, and you decide to tune your garbage collector. And you do this for some front-end server or something. And you tune it, and then you leave for home, weekend, cottage, whatever. Then CPU starts increasing because you have this misconfigured garbage collector. Because CPU is increasing, you start seeing slow requests. You start seeing slow requests, it means that you have to process more requests, which means that you will end up in queuing, which will take up more RAM. It means that given the fact that this is a front-end service and you might want to do some caching on it, you will end up with less RAM for caching, which means that more requests actually go to your backend, which goes to fire. So on one instance change or one service change can lead to a world of hurt. And we've all known this, and we've all seen this. 500s everywhere, CPU memory maxed out, timeouts everywhere. I hope you appreciate the fact that I matched the color of this with the color of the blue screen of that, version 2010, I think. So I'm not sure if it's visible on this. Anyway, so yeah, this is a world of hurt. And this is the world of hurt that's still isolated to one instance. But let's see what happens when this starts affecting other instances. So let's assume that we are more or less in the same scenario, and service B starts misbehaving. Initially, you have a pretty decent distribution of load between service A and service B, or instance A and instance B, but instance B goes down. So what happens? Load gets redistributed to instance A, and this puts more pressure on instance A, more pressure on its resources, and makes it more likely to fail. And this can cascade into affecting all of your backend. Okay, this is another interesting thing, and I think someone mentioned retry amplification earlier. So in this case, we see our service starting to 500, and all this traffic is not the cause for the 500. It's actually a reaction to these 500s, because our clients were configured to just retry without any more sophisticated policy in place, which meant that they actually ended up DDoSing our service. They put more load on our service, which meant it's more likely to throw 500s, which means it's more likely to fail. Sorry. This is another interesting one. So this is basically the number of TCP connections that service A starts when it's calling service B. Usually we use connection pooling, so we're going to use the same TCP connection pool. But as you see here, we started seeing lag, which means that more connections are blocked on I/O, which means that calling services have to start more establish more connections, which means that besides the fact that there is a there is a significant CPU used in actually establishing this TCP connection, which becomes a pain at really large scale. But what I was trying to point out here is that this thing will actually propagate for the calling service as well. So its calling services will end up having more or less the same behavior. Latency will propagate all the way down to your client, and it's going to be bad. Okay, one last thing I wanted to show you from the how not to do things at N26 is resource contention. So we had a situation, this is actually from our staging environment, we had a situation where we were doing some load performance testing, and this caused some instances to max out on CPU. So the load balancer, the auto-scaling kicked in, and it started new instances, but it only started them one at a time. So whenever these instances were started, they would spin up, start receiving traffic, and then die immediately. And it was just like taking your lambs to the slaughter. They had no chance because we weren't actually scaling up fast enough. So it was basically just pointless. The same would happen if you would scale, if you try to throttle traffic. If you don't throttle traffic fast enough, you're going to kill your existing machines in a similar pattern. Okay, so this is what happened to us on various occasions. What did we try to do to prevent it? First of all, let's just look at some strategies to actually improve resilience in these cases. Remember the question I asked in the beginning? This is where I'm coming back to it. Basically, the main reason why, like one of the benefits of actually going for asynchronous flows is that you can implement this interaction pattern called choreography, which means that you will just emit events and let upstream services, or in this case, downstream services, handle these events. This puts significantly less pressure on your infrastructure to deal with these cascading failures, and it makes it less likely to have cascading failures. Wherever you can use this pattern, use it, because it will save you a lot of potential troubles. What about capacity planning? Like, do we still need it for our day and age? Who is doing capacity planning when they launch a new service here? Okay, kinda. So the answer is kinda, indeed, but I would say that, first of all, it's not sufficient to make sure that you have enough capacity to deal with your resources, because you never know exactly how much enough is enough. Also, it's very hard to predict your actual traffic patterns, especially if you launch a new service. So whatever capacity planning you might do, it's probably going to be super highly imprecise. Also, it's expensive because you're going to have people involved in this capacity planning process. You're just like burning developer time for something that might not be relevant, and it's going to be super imprecise. So my advice to you, if you can afford it, just over-provision and move on. And invest time in stuff that's more valuable to your company. And these things are primarily automating and the provisioning and deployment of new instances. So make it super, super cheap to spawn new instances, to kill existing instances, adjust your capacity as you move along, invest in auto-scaling and auto-healing, so make the scale-up and scale-down process automatic so that you can respond to traffic pattern changes. Also, again, coming back to publisher-subscriber, this really helps, because basically you can just put back pressure on your incoming stream of messages and just process them later, even if you don't have enough capacity at this point in time to process them. Of course, there will be lag, but at least you won't end up in a cascading failure situation. Last but not least, and this is super important, know and measure what your SLIs and SLOs are. So make sure that you can predict when you're going to hit capacity problems and try to take action way earlier than that. This is super, super important. Okay. If you do need it, and I've been in companies where we did need it because we had huge traffic and we couldn't just wing it massively, we had to kind of guess an approximate amount of instances that we had to deploy to production. Base it on business requirements. Find out what the business actually wants from that particular feature that's provided by the service, and make sure you have enough capacity to provide that feature. Don't optimize for something that's not really relevant to the business. Also, draw a map of dependencies between your services, and you will have a lot of services going to one particular service. This is a critical service. Make sure you have enough capacity for the critical service and just hand wave the rest. It's fine. The rest can be YOLO'd. The critical services have to be looked after. Also, watch out for seasonality. Even if you're not in, I don't know, you're not an Amazon or a Zalando of this world. And I have a really nice anecdote, because at some point we were actually almost kicked out from AWS. Kicked out is kind of a misrepresentation of what happened, but we were during Black Friday. Zalando, Amazon, a lot of people reserved a lot of instances in AWS. And Spotins was actually at some point trying to scale up one of our services, but because there were so many instances that were reserved in the data center, actually this messed up with Spotins' bidding algorithm. And they were like, oh, we cannot afford to pay this much for an instance, so it refused to scale up. Of course, some of it was misconfigured on our side, but it was a really interesting anecdote of how seasonality actually affected us, even though we're not in the space of shopping in any way. Okay. Also, try to, when discussing capacity planning, try to use some sort of resources, hardware resources, to measure capacity instead of just like doing requests per second. Requests per second are kind of a false god, because requests are super different from each other. Like you cannot say that, I don't know, maybe doing a health check is the same as doing like some very CPU computationally heavy job on your service. So try to kind of measure capacity in terms of how many CPU units would I use for the traffic patterns that I see in this service. Another really important thing that you could do is chaos testing. I'm not an expert in this. We're still experimenting with this internally in N26, but it's a really good way to make sure that in case of something going wrong in your service, you still have the resilience to carry on. And chaos testing means that people do stuff like taking down instances in production, messing with the latency of the network in production. It's really important to also do this in production, because the traffic patterns you get in production are completely different than what you would get in a performance environment or in staging and so on. Look it up. It's really good, and it's going to become more and more popular as time advances. Okay, this one's also something I feel very passionate about, which is retrying. First of all, please, if you provide any kind of service, make your endpoints idempotent. I cannot emphasize enough, because I've had to integrate with partners that didn't have idempotency implemented in their endpoints, and this was a nightmare. Basically, if your request times out, you don't know whether or not you can safely retry, because you don't know whether or not, for example, your request will cause a double write. It's horrible. Please, 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 please. This implementing idempotency makes life so much easier for everyone. I cannot emphasize it enough. Also, don't be clever. Don't do stuff like get with side effects. Don't misuse HTTP verbs to be semantically something they're not. People will expect your get to just do a get and not have any side effects. If the get also does some write in some other thing, it's bad. Please don't. Also, if you can afford to be stateless, please do so. It makes life so much easier. I don't know how to retry in a stateful environment, and this presentation does not assume that you're in a stateful environment. I'm sorry for you if you are. Okay, and sorry. Okay, so another question is what to do with retries, and this is something we're going to actually talk about in a bit. Another really important thing that everybody talks about, but I will mention it here as well, please don't forget to add jitter into your retries. What does it mean? So everybody does kind of some sort of exponential retry, right? Exponential backoff when they retry. But what this means is that you'll end up in a pattern like, in a distribution like this. So you have something that's misbehaving, and after that you do exponential retries, but these exponential retries tend to synchronize, and they tend to cluster in very bursty traffic groups of requests. And this is really bad because basically you're more likely to temporarily overload your service in these bursty instances of bursty traffic. So what you can do is just add some randomness in between retries. So you will get a more even distribution of load across your service, and you're less likely to end up in bursty traffic that's gonna mess something up. Also, implement something called retry budgets. So I think that everybody has some sort of limit to how many times they retry. So for example, you have at most three retries per every request. But another thing you can do is to actually make sure you have a retry budget per instance. So you're saying that instance A calling instance B, instance A can retry at most 10% of requests, or at most 10% of the requests can be retries, which means that anything above that, if you see that you're doing a lot of retries to a service, it's quite likely that this service is unhealthy. So you might as well just throttle the request, don't send them, and move on. And now we're going to get to timeouts. So which one of you is in one of these situations where you have a complete chaos in the way you set timeouts on your service-to-service calls? Really? Everybody's like, okay, which one of you just has one timeout for all service-to-service calls? They just use the default because, okay, it's safe to admit it, because it's happened with us as well. So it's very, very hard, as you probably know, to maintain discipline in how you actually configure timeouts for requests. Moreover, if you have nesting, if you have like service A calling service B, calling service C, calling service D, it makes it even harder to actually make this meaningful, because you're going to end up in situations like this, where you were disciplined up until here, but then someone created this new service, a junior created the service-to-service call that calls service D from service C, and they just set a 5-second timeout because YOLO. And what this means is that if this thing is slow, instances before it that are calling it will have already timed out and potentially retried this request, which means that this thing is just doing unnecessary work completely. So basically, this thing will be overloaded by retries, and the work it's going to do is meaningful because it's never going to end up responding in time for service C. So to be honest, I have no clear solution for this. Maintaining discipline is easy, but if you have more nesting, more services calling each other from different flows, it becomes very hard to actually set timeouts to something meaningful. So there are some solutions in some frameworks that allow you to propagate timeouts. I think gRPC has some support for this, and this is something that you should strive for, because then you could say, okay, service D, you only have maybe 1.5 seconds to complete this request. And in this way, you make sure that you set your timeouts to something meaningful, but there's no silver bullets. Also, for the love of God, avoid circular dependencies. It's horrible to argue about this if you have service D calling service B as well. Like, what kind of meaningful timeouts can you set for this? It's pretty much impossible. Okay. Another thing you can do is to actually set per client limits, which means, remember the thing I mentioned in capacity plan, that you should kind of map your request to actual like some sort of hardware units, CPU, seconds per time, and so on, try to do that. Try to say, hey, all instances of service A, that's calling service B, can use at most 10,000 CPU units, whatever metric you decide to use that's actually mapped to some hardware metric. So service A can only use at most 1,000 CPU units on service B. The problem with this is that you need to actually keep track of like all the instances of service A and all the instances of service B and kind of aggregate all this information about like how many resources service A used from service B. And then whatever resources they use on top of that, you have to throttle. So this is really tricky to implement in practice, and it requires a lot of infrastructure work to do that. So you could still do it based on something like, okay, for every instance of service B can be called by service A at most, I don't know, 10 times per second on this endpoint. So you can still do that, and it's still valuable, and it's still a way for services to push back clients that might be misbehaving and might be calling the service too much. Okay, this brings us to circuit breaking, which is what Hystrix was providing to us. It's a pretty known pattern. I'm gonna just quickly go through it. So you have service A calling service B, and you have something in between that looks at the responses of service B. And if service B returns 500s or times out or something, and if these timeouts or errors go beyond a specific threshold, the circuit breaker will kick in, it will open, and will not let any request go through to service B. Because it assumes that service B is unhealthy anyway, and it assumes that letting requests go through will just make it worse. So this is kind of the finite state machine of how a circuit breaker works. When you're in an open state, from time to time, you will let some requests go through just to kind of poll to see whether service B recovered. If so, you're gonna let more and more requests go through and eventually reclose the circuit and let the entire traffic go through. Sorry. This is gonna turn into an ASMR talk. You know ASMR? Like this thing where people eat pickles on very high quality microphones? Never mind, look it up. Yes. Okay, so this is another thing, and it's kind of like a new kid on the block that's actually used by Netflix, and this is what they're replacing Hystrix with. I'm gonna talk about the actual tool in a bit. And it's called adaptive concurrency limits. And it's working with the assumption that basically most servers will have will implement a model such as this. So you have concurrency, which is the amount of requests that you can actually process in parallel. And you have queuing, which is requests that cannot be processed at this time, and they will queue up to be processed later. And the main assumption that this method uses is that when you have queuing, you will also have lag. When you have lag, it means that you have to kind of throttle the request you're sending to the service. So it does this by actually this formula. It's not that complicated. So it establishes this variable called gradient, which is the ratio between the latency when you don't have load, so the ideal case latency where everything's fine and the service is not overloaded, and the actual latency now. And if this is smaller than 1, you'll see that this limit will actually decrease. So it's just like current limit times gradient plus some sort of fixed queue size to account for bursty traffic. And you'll end up with like this nice seesaw kind of pattern where it just keeps trying to push for more requests, and after that backs off, and after that pushes for more requests and backs off. Okay, last but not least, what can we do in case we actually mess up? In case, like service B is completely unresponsive, it cannot do anything. And this is actually a trade-off that you have to discuss with your product owners, because the cost of implementing these things is going from high to low, but so is your user experience. So basically, if you implement a cache, you might not even have any user impact whatsoever. Like in this case with that I showed you before with what my colleague was trying to fix, If we couldn't get the country for a user and we use the cache, it's probably fine because the country rarely changes, so it's okay. If you have writes, you can also use the dead letter queue, so you just queue the writes for later, and after that, move on. You can return a hard-coded value, and Hystrix slang, this was called a fallback. If you're Netflix, for example, let's say that you have a service that returns movie recommendation, you can just return some sort of standard movie recommendations, even though they're not specifically tailored to the person. You can just return super popular movies, and that's it. Worst case scenario, you can just return an empty response, fail silent, or just crash, and the user will actually see that your infrastructure is not very resilient. But again, make sure you discuss these with your product owner because it's a drawback. It's a cost to benefit discussion, and you have to have it with product people. Okay, so this takes us to what kind of tools can we use to improve this resilience. So basically, I gave you some things we were trying to implement, and these are the tools that we looked at for implementing these techniques that I mentioned earlier. And I'm going to start with Hystrix, just to make sure that we're on the same page. So as you know, Hystrix is just a Java library. You just import it as a jar, and basically it sits inside of your business logic, and it protects any outgoing request from code. Basically, it implements the following features. So it has support for timeouts. It's primarily a circuit breaker, right? So it needs to have some sort of knowledge of timeouts, of obviously circuit breaking. It also has really nice support for fallbacks, and does this thing called response caching, where you can actually not repeat the same request twice. So if you're doing 2 requests to get the user information in the scope of the same request, you can configure a cache, and you can say, okay, I'm not going to do the same request twice, because in the scope of a request, it's unlikely that the user information will change. So it does this, and this response cache also makes it easier for you to provide a meaningful fallback. This is what it looks like. I'm not going to go through it in too much detail, but this is the cache key that I was talking to you about, and this is something that will end up in a lot of problems if you misconfigure it. This is the actual call to the user info API that's protected by Hystrix. A lot of stuff, you probably know how to use it, so I'm really not going to linger too much on this. Observability is actually pretty good. It has this tool called Turbine that aggregates data from all of your circuit breakers and actually allows you to generate these super nice graphs. Testing is relatively straightforward, minus the configuration needed for this cache. That can be a pain in the ass sometimes. But otherwise, you can do whatever type of unit integration tests you need. Okay, but the bigger problem is that it's no longer supported. So this is why we actually having this talk. This is why we decided to move away from it. Basically, for us, Hystrix is no-go anymore. It's also not language agnostic, so depending on how your backend microservice architecture looks like, and if you have a polyglot backend, you can only use Hystrix for Java or JVM-based languages, which is not great for everyone. Two more really important things that I want to mention. First of all, it forces you to build thick clients. So we discovered when we first started using Hystrix that many people were misusing it. So we said, okay, cool, let's just build a library that gives you a pre-configured Hystrix with retrying pre-configured everything for all of our services. Yeah, cool, but Hystrix has a ton of dependencies. It has a lot of transitive dependencies, and this results in a lot of versioning conflicts whenever you import maybe two different clients that are configured in the same way, but have dependencies on different versions of Hystrix. And this was one of our main challenges with Hystrix, and it's something that we wanted to avoid in the future, if possible. Another thing was that it's very tricky to enforce it on calling services. So it's very tricky to say, all calling services calling my service will implement this in their logic. Because as you've seen, it's not trivial. So we had a lot of people just circumventing this and conveniently skipping Hystrix, which was not great, and it meant that we were not protected in case of a cascading failure. So another alternative is Resilience4j. So Resilience4j is kind of like the solution that Netflix advertises if you want to continue using the same patterns and if you want to continue using circuit breakers. It's very nice. It's very feature. It has a lot of features, as I'm going to show you later. It has the same integration pattern as Hystrix, so you just like download some jar, and after that, you need to decorate a lot of all of your service calls inside of the business logic with some Resilience4j artifacts. It has a lot of features, and it's nice because it's a bit more modular, so it adds more and more features every day, and you can just use whatever you want. It will even add adaptive concurrency limits at some point in time, but they don't have a clear timeline yet. So if you look at the features themselves, it's really, really feature-rich. If you want to learn more, there's actually a talk during lunch. It's called Hystrix is Dead, Now What? And it focuses specifically on Resilience4j, so I advise you to go there and check it out. It's basically, it implements everything as a decorator. It's just an implementation of the decorator pattern. You can kind of mix and match these decorators however you see fit. It's really easy to use. Again, quite similar to Hystrix in terms of complexity of adoption, but with some nice things. It has support for everything under the sun in terms of observability, so you can dump your data about open circuits anywhere you want. It also has really nice ways to plug into various events, so you can log, alert, whatever, send information to Datadog whenever some super specific event occurs. Testing, similar to Hystrix. And it's actually quite different to Hystrix when it comes to how thick the clients that you would end up building with this would be, because Resilience4j, the thing they got right is the fact that it has very few transitive dependencies. So if you want to follow the same pattern, Resilience4j is the way to go, and it's going to lead to thinner clients, which is quite nice, but it still forces you to build thick-ish clients. So you'll still end up in with, sorry, you have a question? Oh, it's fully open source, so use it as you please. I don't know exactly the exact type of license, but you shouldn't be constrained in any way. I think you can use it commercially. It's also modular, as I mentioned, so you can just use whichever part of it you want. But on the downside, it's also not language agnostic, so no bueno, if you're in a polyglot environment. Which takes me to Envoy. So, as you probably know, Envoy is a really hot and sexy proxy right now. A lot of people deploy it in service meshes as a sidecar that sits close to their actual service instance, and they route all traffic going in and out of the instance through Envoy. So Envoy has a lot of cool resiliency features. It has everything that I mentioned here, plus they're working together with Netflix on building adaptive concurrency limits as a first-class citizen in Envoy, which is pretty cool. But the configuration looks like this, and this is a very basic configuration that applies one particular circuit breaking policy to pretty much everything. Wait, yeah. See, like this prefix -all means that this thing will be applied evenly across your entire service mesh. And if you want to go into some more complex fine-tuning of like, okay, this route needs to have at most 2 retries, and the circuit breaking policy needs to happen this, like this, and that, it's going to be a pain in the ass. Sorry. So this static config is one way to configure Envoy. It's probably not the most scalable way. And even if you choose to go with static configs in the future, you will need to provide some sort of automation to generate these configs, because otherwise it's going to be a massive, massive mess. What they provide, and which is really, really cool, is something called like dynamic config API or whatever. I don't remember the name. But it's a way to actually configure all of your Envoy instances on the fly without any downtime. So you can do a hot swap of the configuration and it just like applied immediately. So it's really, really cool, but you'll still need some tooling for that. If you want to manage it properly, you probably need a control plane like Istio to do it. We don't have too much experience with Istio yet. It's something that we're evaluating just because configuration, using static configuration is something that does not scale for us already. So stay tuned. I'm going to probably give another talk about how Istio helps with all of this. Envoy is super feature-rich when it comes to monitoring, and it sends a shit ton of information to any data sync you might want. You can identify whenever your circuit was open. You have metrics for every single thing. It's one of the main selling points of Envoy. It's like really, really good from the observability part. Setup for a test can be tricky. You kind of need to run integration tests for this. You need to spawn a Docker container of your service, a Docker container of your Envoy, and kind of call your service through the Envoy Docker container and make sure that it does what it does. This being said, if you have everything containerized, it shouldn't be too hard. So what are the main selling points for this? Language agnostic. So if you have Node servers, Java servers, Kotlin servers, whatever servers, PHP, I hope not, servers in your backend, this could help enforce the same kind of policies across all of your polyglot microservice backend. It's language agnostic, so yeah, you can do that. It's also easier to enforce a specific policy on all of them. So remember I told you that our biggest problems with Hystrix was the fact that it was very hard for us to enforce it on calling services because some developers might forget to actually include it when they develop a new feature or a new service call. So with Envoy, you can actually enforce it centrally, which is great. It's harder to configure, but great that you can actually enforce it. You can also do dynamic changes to it. So for example, let's say that you have some service that's misbehaving, or you realize that you misconfigured some limits to something and you're throttling services when you shouldn't be throttling, you can actually take dynamic action without having to redeploy your services. You can just say, hey, yo, stop doing this, and it will be applied immediately, which is really good. Also, you can do it both on the caller side. You can protect both the caller side and the callee and service side. It's really versatile and really useful. And also observability is really good. In terms of negative parts, yeah, it doesn't support fallbacks and caches, so you'll have to implement this in your business logic. And testability is tricky. Operationally, it's tricky. And it also falls in this gray area between SRE and dev. And depending on how you structure your development teams, this might be a problem because you might not really know who owns the circuit breaking policy of your services. If you have like a clear separation between SRE and dev teams, then this is something that will fall in the middle. Okay, and last tool that we looked at is concurrency limits from Netflix. This is basically an implementation of adaptive concurrency limits, the thing I spoke earlier about. It's also jar. You can use it both on the client side and on the server side. So it's pretty cool because even if it's a jar, you can say, okay, I want to protect my service against abuse from any other service, so I can just use this on the server side and not worry about whether or not all the callers implemented circuit breaker or something else. So as the name suggests, it's just like does one thing and not one thing well. So it implements adaptive concurrency limits. It's really easy to configure, actually. This is actually a configuration for the server side, and it's just a few lines of code, and that's it. And this will, obviously you can configure it in more detail, have different policies for different routes, but this is like a bare minimum, bare bone configuration that you can do. Sorry for the code. This is a bit of a convoluted Kotlin code, but it also provides a lot of hooks to actually implement monitoring however you see fit, detect all sorts of events happening to the library however you see fit. So observability is fine. Testing is tricky, and also identifying when you actually get throttled is also quite tricky, so good luck with that. I don't have any experience with how to test this, and if you do, please tell me, because by nature, it's kind of unpredictable, right? It's kind of unpredictable how it's going to adapt limits, and I don't have any meaningful tests that I've done so far for this. Unfortunately, it's not language agnostic. If that's a problem, well, then it's not the way to go. The main reason why we're a bit wary of this is that documentation is still quite scarce, and there's not that many stories of it being used in practice. So it's still a young library, and I'm sure that Netflix has done a great job, and I'm sure that they're going to post a lot of more information about all these topics that are still unknown. But I think it has a really good future ahead of it. So the question on everybody's lips, what did we go for in the end? This is the list of stuff we looked at. There's two more things that I haven't mentioned in the talk. One of them is gRPC, which you might find weird, but you should know that gRPC is actually working on, or at least they have a proposal for implementing a lot of this resiliency features into the client stub that it generates for service-to-service calls. So you might see in the future that gRPC comes with a lot of this functionality built in, which would be really good, especially if you've already adopted gRPC everywhere. Sentinel is a library that does pretty much the same as Resilience4j. Unfortunately for us, it was developed by Alibaba, so a lot of the documentation is in Mandarin Chinese, and we couldn't really use it, so we kind of ruled it out quite early on. So, want to place some bets? What did we go for? Yeah. So we did go for Envoy, and even though Resilience4j is very feature-rich, for us it was very important that we could implement resilience features in a centralized manner, so we make sure that it is really applied everywhere across our entire infrastructure. We already are using it for gazillion different reasons, and there's lots of benefits to going for Envoy that I'm not going to talk about now, but we can have a chat about after the talk. And it allows us to basically make these changes completely transparently to the callers. So you no longer have to implement all these things in your business logic, which is great. We still needed something like retries and timeouts sometimes, just because we're not super advanced in how we configure Envoy yet, and we cannot really define these on a very granular level with our current Envoy configuration setup. So we agreed that at least for retries, caching, and fallback, people can still use Resilience4j, and this is fine for the time being. Okay, questions? Yes?
So you implement your own infrastructure, so you need your own solutions, but how would you come up out of the box solutions provided by Google or Amazon, which solve those problems of deploying multiple services and doing the fallback? Do they provide
Not that I'm aware of, because it's very hard for them to set meaningful timeouts, for example, for you. They don't know if you have a legitimate case to have a 10-second timeout as opposed to a 5-second timeout. So to my knowledge, they don't really provide this as like a built-in first-class citizen in their infrastructure.
So there is a level, and when you pass the level, you need to do
Kinda, yeah,
your own.
pretty much. I'm going to be available after the talk, and we can meet for lunch and discuss if you want. But thank you.